let's start, okay? First announcement, we're going to have a makeup session on the Saturday. So this Saturday from 2:30 to 4:10 p.m. Is this time okay for everyone? This Saturday, 2:30. So in this case, C is a common effect. Now, the common effect is in this case, there's no correlation. Okay? They're completely independent. However, if I decide to condition on it, well, the reason why they are completely independent is because this is a collider. Right? So there's a path, but this is a collider. And once the collider, this is blocked. They're independent. In other words, we say they're de-separated. Now, if I condition on it, means if I fix the level C, only consider the level C condition on C equal to 1 or C equal to 1, right? Condition on C, then this path is unblocked. So in this case, it is this is the open path, and A and B become correlated again. Okay. So 3 reasons why A and B may be correlated. Okay. So let's focus, but in particular, on this case, in which we have a C, and C goes to A, and C goes to B. Okay. So let's focus on this particular case. In this case, C is also called, well, C is a common cause, but it's also often called a confounder. Okay. So the word confounding, right? Confounder. Okay. So whenever we have a confounder, the correlation between, now, suppose I'm interested in the causal effect of A and B. I know that A may have some effect on B. Okay? But I'm not sure. I just think there may be some correlation, right? There may be some causation. However, in this case, the correlation between A and B will not tell me the causation. Because in addition to direct causality, there is this path open, okay? In which case, it will also make A and B correlated. So without blocking this path, then the correlation between A and B could be due to this one, or could be due to the direct causation. Right? So that's why C in this case is called a confounder. In the existence of a confounder, the correlation doesn't tell us causation. Now we can also write it this way. We say the probability of B, okay, conditional on A. So this conditional probability tell us the correlation. But I'm interested in the probability of B conditional on do A, okay? I'm interested in this one, which is the causation, the causal effect of A on B. If there is a confounder, then they are not equal, okay? The correlation is not equal to causation, right? If there's no confounder, okay? If there's nothing, only A and B, then the probability B and A will directly tell you probability B of do A, in the sense that the correlation will be exactly tell you the causation. Right, so that's the idea, okay? Now, one of the most important confounder in economics is so-called self-selection effect, right? So self-selection is a special type of confounding. Now, what self-selection is, so let's consider, okay? Suppose we, again, using the language of treatment and outcome. We consider the treatment X, and we consider outcome Y. Now, we are interested in the treatment effect on the outcome, okay? However, if X is selected, when people select their own treatment, right? When people select their own treatment based on a variable Z, okay? Now, if people choose the value of X based on Z, then there is a line like that. And then if Z also happens to have some effect on Y, then there will be a link like that. And then Z is a confounder. And so we have a confounding issue. Right? So self-selection is a special type of confounding. Now give is for example, right? So again, X will be education at college, and Y will be earnings. Now we're interested in the causal effect of X on Y, but if people choose their education Now, in a way of choose, but people get into college or not get into college because they have different ability, right? So now Z could be just ability, right? So ability will be a confounder. Ability affects your probability of, affects whether you get the college treatment or not. And certainly ability also affects your earnings. And in that case, we say ability is a confounder. Now, in the existence of such confounder, the correlation between education and earning do not tell you the causation. Right? Okay, so this is a very simple way of using the graph to represent, what we talk about in terms of causality, endogenous selection, etc. Now, here this ability in reality is often unobserved. Okay, it's often unobserved. But if we assume, all right, if we assume that all the confounders, so this Z can be multidimensional, okay? It can be Z1, ZP, okay? There are many Z that are confounding, okay? Numbers. But if we assume, right? If we assume that all the Z's are fully observed, that we see them all, in this case, we say there is selection on observables. Okay? How many of you have heard this term in econometrics? Maybe. Okay, all right. So selection on observable means that we have observed all the confounding variables. Right? So that's what it means. Now in statistics, when people talk about causal inference, there's another saying which says no unmeasured confounding. Right? So so every confounding has been measured. We see them all. When Z is not fully observed, we say there's selection on unobservables. Okay? So some selection happens on unobservable. So some Z are not observed. We don't see them. But there's still selection in fact. Or there's still confounding. In that case, we say there's selection on unobservables. Or we say there is some unmeasured confounding. Okay, some margin that's not measured. Okay. Now before continue, I just like to go back slightly. And let me just say a little bit notation-wise, okay? Now, the type of graph we're talking about, right? We call it causal diagram. So I just want to give because this is in the appendix, I'm not going to go over all of them. It's very interesting. You should go over if you're interested. But the causal diagram theory, first of all, it's a graph. Well, we're studying here, this kind of thing. Okay, it's called a graph, right? And a graph is a mathematical construct, all right? And a graph consists of nodes, okay, also called vertices, and also consists of links, called edges between the nodes. And we can use this kind of graph to represent many things. For example, you may often see people use this kind of graph in social science to represent social networks. Okay, like this person has a link to this person has a link to that person. Some people often ask me questions about social network, thinking they're neural networks. It's a completely different animal. Okay, no relation to each other. We don't have time to talk about neural networks in this course, but a neural network is not a social network. Anyway, so this is called a graph. Right? Now the graph may not have a probabilistic interpretation. However, if I first thing, if every edge, okay, so if every link between the nodes has an arrow, okay, so if every link is directed, it's called a directed graph. Now, if the directed graph also has no cycle, what do we mean by cycle? Cycle means z goes to a, z goes to x goes to y goes to z, like this. Okay, this is a cycle. If there's no cycle, we say it's directed acyclic graph, also called the DAG. Okay, so the reason why I especially want to mention this is because maybe some of you, or maybe in the future, you will see many DAG. So DAG, okay, so DAG means directed acyclic graph. It's a very useful term. So this kind of graph is called a directed acyclic graph. All right. Now, a directed acyclic graph, DAG, in which every node represents a conditional probability, okay, is called a Bayesian network. Now, what does it mean? So, if I have, let's say, A, B, C, all right? Actually, let me write it this way. B, C, A, okay? And then B goes to A, C goes to A. Now, if I only have this relationship, it's a DAG. But I don't have, it doesn't necessarily have a probability distribution associated. But I can put the probability distribution onto this DAG, all right? And then specifically I can say, okay, the probability of A, B, C, all right, can be written as the probability of A conditional on B, C, probability of B, probability of C. If I say, okay, the joint probability can always be written this way. Why? Because the graph tells me that the probability of A, the graph tells me one side conditional on BC, conditional on B and conditional on C. The probability of A is fully specified. Okay, so once I can write the probability A conditional on BC, and that's it, because the conditional probability is specified by B and C, and then B has no parent, C has no parent, so I can just write PBBs. Okay, so this graph tells me that this joint probability can be written this way, can be decomposed into PB, PC, and PA conditional on BC. If I do this, then this type of structure, okay, this type of model is called a Bayesian network. A Bayesian network. Right, so that's the second concept. So what is a causal diagram? A causal diagram or causal graph is a Bayesian network. First of all, it's a Bayesian network because we're going to use this graph to represent the relation between different variables in a causal way, and their joint distribution will be specified by a relation like this, which is, the distribution of A, the probability of A will be fully specified by B and C. The condition on B and C is fully specified. Okay, so that's our interpretation. And the second, the link in a causal graph represents causality. So a causal graph is a Bayesian network in which the link represents causality. That's it. Okay. So you can think about the causal graph that we're introducing in this class as essentially a Bayesian network, which is a DAG with a probability distribution attached to it, and the link represents the direction of causality. So that's what causal graph is. First of all, why does causal graph have to be a DAG? Now, a DAG, remember, is a graph where all the links are directed. Now that's easy to understand because in a causal graph we want to represent causal relation, so we want every link to be directed because we want to say, okay, you cause this, you cause that, okay? So it's directed. But why acyclical? Why acyclical? Why we cannot have this thing? Well, it's because it's impossible in causality. In causality, you cannot have B cause A cause C, C cause D. Okay, it's just impossible, right? You cannot, because in this way it means B cause itself. There's no such thing, all right? So in trying to represent causal relationship, it has to be acyclical. That's why we use DAG, and we put we both use a DAG to represent, to specify the joint distribution, also to represent the causality. So that's what causal graph is. Okay. So just sign up. All right. Let's go back. Okay. The next concept I want to talk about is identification. Now, in this course, when we're talking about the first part, right, the statistical modeling part, most of effort has been estimation. So we're trying to estimate model, or we're trying to learn the model, right? Learn just means estimate. Same thing. You run a model, which is an estimated model. We haven't talked about identification, but of course, I'm sure all of you have heard the term identification out. This is identified, this is identified. What does identification mean? Now, identification, if I want to give you a more sort of slightly rigorous, many ways to do it, but a slightly rigorous, semi-rigorous definition of identification is that if I give you a causal model n, okay, there's a model n, and the model m has n different variables, like x equals x1 to xn, and but I do not see it. I may not observe all the x. I may or may not. Okay. Now, what I observe is the variable v. Okay? So v is the actual variable I observe, and the v can be the same as x. Okay? They can be the same, or they can be different, or they can have significant overlap. Right? But let me just say v is what I observe. X is the variable of the model, right? Okay. So suppose I'm interested in a function of x. Let's say gx. Okay. This function is based on the underlying model x. All right. Now I'm going to say that this function is identifiable if based on observation of v. So you can think of the function as a function of this model m. Right? So it's a function of x and can be derived based on this model m. So here's the idea. We are interested in a model m with variable x, but we only observe v. So the question of identifiability is whether we can actually get out, okay, whether we can actually get what we want, which is the model m with variable x. Can I get it? Okay, can I actually back it out from the observed v? That's the question of identifiability. So you say, wait a minute, because in reality, you say, okay, we observe v, but how much do we observe? Like, what is the size of a data point? What is the size of a data? How many data points do I have? Okay, do I have a small data set? Do I have a large data set? Well, we don't care. The question of identifiability, you can think about the question of identifiability is this way. Suppose I see the universe of v. Okay, suppose I just have an infinite data set. I see the underlying population of all the v variables. Can you tell me what, this function of x looks like? Can you help me pin down it? That's the question of identifiability. Okay? Let me try to give you some examples. All right. Actually, let me just say this. Now, M may not need not be a causal model. But suppose M is a causal model, okay? And it has variable x. And let me just say, so I said, okay, this function of x. Suppose this theta, which is a function of x, is the causal effect of one of the x variable on the other x variable. Okay? So we have a model M, and M has maybe x1 to xn. Now, let's say x1 and x2 are two variables in this model. The causal effect of x1 on x2. The causal effect of x1 on x2, you can think of that as a what? As a function of all the x variables, right? The causal effect is a function of all these things. The question of whether this causal effect can be identified is the question of, can I actually estimate it? Can I estimate it, or can I guess something about it, know something about it? Can I uniquely determine it if I observe all the v? What is v? V can be anything, okay? V can have nothing to do with x. V can be z1 to zm that is completely different from all the x. In that case, you probably never be able to know this. But v can be x1 to xn. Okay, v can be the same as x. Well, in that case, if you see all the x, of course you can pin down. Okay, you can pin down this function. What if v is x1 to x10, but then anything after x10 from x10 to xn, I do not see. If that's the case, can I still get the function out? I'm not sure. Okay. So again, so the question of identifiability is whether I can uniquely determine something suppose I observe the underlying population of all the data I see. All right, so we'll give more example later. Okay. All right. Now, on a causal graph, okay, what is the effect of doing an experiment? Suppose we have this kind of causal graph. A and B goes to C, C goes to D. All right. Now, if I tell you that I'm going to do some experiment and I'm going to set the value of C to something else. Okay? So I want to know, what if I do C equal to 1? I want to just manually change the value of C. How does this change this causal graph? Well, the result will be, okay, if I manually change it, it's actually very simple. The result will be the link from A and B to C are completely broken. So now it becomes something like this. Now I hope this is easy to see. Why? Because in this causal graph, we say C is determined by A and B, right? But if I go in as an experimenter, I manually change the value of C, then C is determined by me. Okay? So determined by me. It's no longer determined by A and B. So now we have this kind of causal graph. So in other words, when you are doing experiments, okay, when we're doing randomized trials and stuff like that, you can think about, what we're doing is we're changing the causal graph. Okay? So this will be the causal graph that describes the relation in the observational data. This will be the causal graph describing the relation in what? In my experimental data. Because in the experiment, I set the value of C. No longer depend on A and B. Okay? So that's one way to think about it. Now, so here, one thing, if you remember, by the way, so this is called pre-intervention, because pre-experiment, pre-intervention graph. This would be post-intervention graph. If you remember, we have a definition earlier. Last time I talked about, I said in a graph, nodes or variables that have no parents are called exogenous, and if they have parents, they are called endogenous to this graph. Okay, to this graph. What you see here will be, once you do the experiment, C, okay, goes from endogenous to the graph to exogenous to the graph. There's no parents anymore. Okay, so so when you're doing experimentation, when you try to when you assign the treatment yourself rather than let it be decided by observation data by some other factors, you are making the treatment exogenous in that sense, right? So this is reflected in the graph terms. Okay. So this will be another sort of illustration where Judea Pro, who wrote about this causal graph, right? So this is from his book. He says intervention is like a surgery, or experimental manipulation is like a surgery in the sense that it basically gets rid of the errors, right? So initially, suppose we are talking about the effect of tax, okay, on the economy. Then I can say, okay, there are always some economic condition that motivates a tax change, okay, that motivates a tax cut, motivates a tax increase. So some economic condition could decide the tax level. Economic condition could also lead to economic consequence, and taxation will lead to economic consequence, of course. So if I want to know the causal effect of taxation on the economy, and suppose I can do randomized experiment, of course I cannot, but suppose I can, then it's similar to basically deleting this arrow, so that tax is completely exogenous. Okay, it's determined by me, the experimenter. So then this tax becomes exogenous. Okay, so we only have this kind of graph post-intervention. So this is almost like a surgery in the sense you're deleting the arrows into the treatment. Okay. All right. So now let me say this. All right. Remember I said the causal inference can be divided into two kinds of tasks. The first kind of task is what I call causal effect learning. The second is called causal mechanism learning. The causal effect learning is easy. The causal is relatively easy. Mechanism is harder. So let's first talk about causal effect learning. causal effect learning is the goal of causal effect learning is to learn or is to estimate the probability of, causal effect learning is given a graph. I give you a graph and I say, okay, there's a variable x, there's a variable y, and there may be some other variables, z here, w here, q here, whatever. Okay, there are many variables in the graph. But my main interest is to estimate the causal effect of x on y. So my goal is very clear. I want to know the causal effect of x on y. In that case, what do I want to estimate? Well, in the end, I want to estimate p y given do x, okay? Or, for a more limited goal, ey given do x, right? Because this is the causal effect of x on y. So I'm either interested in estimating this, which is a more limited goal, or I estimate the entire conditional distribution, or py given do x, okay? All right. So one way we can think about causal effect learning as, what I'm saying here is causal effect learning, one way to think about it is basically the same as statistical learning. But in statistical learning, our target function, remember what we're trying to learn when we're doing statistical learning. Our target function is oftentimes ey given x, right? So when we are, when I'm in my introduction, when I'm talking about the foundation of statistical learning, I said, okay, one of the, the most typical task in statistical learning is our target is ey given x. Given the x, I want to predict y. Okay? And one way to think about causal effect learning is our target is not ey given x, but ey given do x. Okay? So it's really that, right? Or py given do x. That's our target. Okay? So you can think about causal effect learning as statistical learning with this ey given do x as the target, rather than ey given x as the target. Right? We're interested in the causal one. Now, given, so what is py given do x? Well, we can always write py given do x, okay, as this. First of all, let me just say, suppose there's an x, okay, and let's say this is a y, and then x may have some causal effect on y. But we also know that y is also caused by many other things. So there may be some z here that also cause y. Now, I don't know about this, but I know z cause y, okay? I know v may cause y, etc., etc. There may be many other variables that cause y, okay, that cause y. So, I can always write, so I'm going to name all these other variables. I'm going to name all these other variables. I'm going to call it sy, okay? So indicating other variables that may have an effect on y. So I can always write it this way. Py given do x is py given do x. And also conditional on this sy. So some other variables that have a causal effect on y, okay? And then p sy d sy. So I can always integrate with right to this, okay? Right. So this is pretty straightforward, which is the causal effect of x on y is the causal effect of x on y conditional on sy. Sy is any other things that can that leads to y, okay? That have a causal effect on y. Probability sy is integrated with right to y. Okay? So that's pretty straightforward. However, one thing that I want to say here is this. What is this sy? Sy is any other thing that can cause y. And this sy is actually the set of potential effect modifiers. Okay, what do I mean by that? Remember, we talk about effect modifier. Effect modifier is anything that can change the causal effect of x on y. Okay, so again, if x is fertilizer, y is output, like y is if this is fertilizer, y is crop output. What can the effect of fertilizer on crop? What can change it? Like, it depends on what condition. Well, it depends on temperature, right? Okay, depends on temperature. But what is temperature? Temperature is, in causal graph terms, temperature will have a causal effect on crop output too, right? If temperature has no causal effect on, if temperature has no effect on crop output, it will not be able to influence the effect of fertilizer. So temperature changes crop output, and fertilizer changes crop output, and actually these two effects are interacting with each other. That's why temperature can change the effect of fertilizer on crop. Okay, so temperature is a effect modifier, in the sense that this causal effect depends on this one. Okay, now. So it turns out that, so here's one of the weaknesses of graph. The graph cannot represent, the causal graph doesn't have the ability to represent interaction among different variables. In terms of, so this variable caused this y, fertilizer caused y, but suppose the effect has some interaction, meaning the higher the temperature, the more the effect here, or the higher the fertilizer, the more the effect here. There's no way for the graph to capture that. But let me just say, okay, if there is interaction, then this thing becomes a effect modifier. But all effect modifier are actually, so what are effect modifier? All effect modifier has to be other causes of y other than x. They have to be causes of y too. So it's all captured by the sy. So sy is the other cause of y other than x. And if there's any effect modifier, they have to come from one of the sy's. So that's why we can always write it this way, where the causal effect of x on y is the causal effect of x on y conditional on any other cause of y, including any effect modifier. Okay? So once the distribution of the effect modifier changes, this thing changes. So, and the integration can change. Okay. All right. So that's all the basics. I want to go over. So now let me just say, okay. So once we, for this introduction, what I can say next is the causal effect learning. We can summarize it as basically as a two-stage step. Okay, as a two-stage process. Once we want to estimate causal effect, we have this two-stage thing. The first stage is called identification. The second stage is called estimation. And the first stage, identification, is a pure causal reasoning step. There's no mathematics, there's no statistics, there's nothing involved. Only causal reasoning based on the causal graph. The second stage is estimation. Now the second stage is based on the first stage. Once we complete our identification using causal reasoning, then we can pick a statistical model to get the effect out. Okay, so let me go through them one more. Right. First stage, identification. The identification question is it possible to learn the causal effect from our observed variables? That's the identification one. Remember, just now I give you a very general definition of identification. The general definition is, I'm interested in a function of x, but I only see variable z. Can I uniquely determine that function from the variable z? Here we have a more specific. Okay, here we're interested in causal inference. In causal effect learning, the identification question is simpler. Okay, it's a simple way of saying it, which is if I only see my observed data, which is v. Okay, and suppose I know the entire population. So the sample size is infinity. I see all the underlying population of my observed variable. Can I actually learn the causal effect? Is it possible to learn the causal effect? That is the identification question. So that's the question we need to first answer, and in order to do the second stage. Okay. All right. Now another way to put it is this: we are interested in learning py given 2x. This is our goal. This is the causal effect we're interested in. However, we only observe v. Okay, our observed variable is v. This v can be, can include x, can include y, can include many other variables, but this is my observed variable. So the identification question is: can I uniquely determine this? Uniquely, by observing the distribution of V, right? So because I assume that I observe all the V, the underlying population, I observe any. If I do that, can I actually uniquely learn the the probability of Y given to X? If it is possible, then we say this causal effect is identified. If it's impossible, then this causal effect is not identified. Okay? If it's not identified, nothing we can do. But if identified, then we can go ahead and try to estimate it. So that's why we say it's a two-stage process. Okay? Right. How do we uniquely determine this from observation of V? Well, if we can express this in terms of probability V, then we are done. Right? So I will talk about this more. Okay. Now, by identification, we can further sort of define, we can further sort of classify identification, two kinds of identification. So one kind of identification is called non-parametrically identified. What do we mean by non-parametrically identified is, suppose I observe V, okay? Can I uniquely determine this from V without making any parametric assumption? If that's the case, then I say it's non-parametric identified. If I have to make parametric assumption on V in order to uniquely determine this, then we say it's only parametrically identified. So now it must seem very confusing, but no worries, because that's what we're going to do. Okay, we're going to talk, give you examples, and walk you through what all this means. Okay. So that's the first stage. Okay, so I'm just lining out the procedure. That's the first stage. First stage is identification. Now, once we are sure that we can uniquely determine this from V, the next question is how. How do I get this out? Okay, so I know that I can get this from V, but how do we estimate it? That's the question. So the second stage is estimation. The estimation question is, okay, so I know that if I have if I know the true distribution of V, then I can uniquely determine this. But in reality, we do not know the true distribution of V. In reality, we only see a limited sample from V. Now, in that case, I can only estimate, right? So how do I do this? That's the second stage, the estimation stage. Okay. So in other words, as we will learn, okay, don't worry if you are confusing now, because we're going to give you examples, but as we will learn, causal effect learning is two-stage. The first stage is identification, which is based on the causal graph, we are going to argue whether we can uniquely determine this by observing all of V. The second stage is, in reality, we only see a limited sample from V, so let's estimate it. But using what model? Like using a linear model, using a neural network model? What model do we use? That's the second stage. That's the estimation stage, which we use the statistical model that we have learned. Okay. All right. So, do we understand this? Okay. Now, let's think about this. So, our target is py given to x. Okay. Like I said in my introduction, the easiest way to try to learn this is to directly do an experiment, right? If we do an experiment, then what is our V? Okay, so the V is our observed data. If we do experiments when we manually set the value to x and observe the y, then our V will be x, y, because we observe the x and we observe the y. And furthermore, what is the probability, what is the distribution of V? The distribution of V, especially what is the distribution of y in our data? The distribution, the py given x, what is that? That is this thing. Why? Because the data are generated from this distribution. Because why? Because the data is generated by do A, do x, and observe y. Okay? So the observed distribution is exactly what? Exactly the target distribution that we're interested in. So that's why experiments give you the causal relation, right? Okay? So that's just another way of saying the same thing we have said before, which is once you do experiments, you directly get a causal effect out of it. is the way that we're saying here is we're interested in py given to x. But then we just do it. Okay, just do it. Just do x, see what y is. In that case, the data you generate and the data you observe is the distribution directly is the same as this one. Because we're do x and do y. So in this case, first of all, is it identified? Yes, of course, our causal effect is identified. Because if we can totally observe the distribution of v, then we totally see this. The second question is, once it's identified, can we estimate it? Yes, we can estimate it. Now, in reality, we generate a limited amount of data, limited xi and yi. You can pick any simple statistical model to estimate this thing from your experimental data. So, that's just a restatement of why experiments work. All right. Now, let me slightly jump ahead. Okay. So the experiments is the easy case, but the observational data, things get a little bit more complicated, okay? Like we said already. So for observational data, how do we get py given to x? Okay, how do we get this from observational data? Let's see, x and a y, okay? Right. And let me just write all the variables that can cause x as PAX, okay? So x may give rise to y. Now, in experiments, there's no PAX. In experiments, if we manipulate x directly, all link is broken. So x becomes exogenous. But in observational data, x is going to have some kind of parents, okay? So some parents are like PA, x will be a. Okay. Now, it turns out that one thing that the graph will be able to tell us is that this py given do x, you can always write it as py given, so suppose do x equal to a, right? So always write py given x equal to a, okay? And conditional on all the PAX and PA distribution, okay? The F distribution and PD PAX and integrate, okay? So in observational data, things are slightly more complicated, but it's not really that difficult in the sense that if we observe all the parents of x, then the causal effect of x on y can be actually written as the probability of y conditional on x equal to a, do x equal to conditional x to a, but conditional on the parents. If we conditional on the parents and they integrate with respect to parents, we can get the causal effect out. Now this is actually a theorem, but I'm not going to prove it, okay? So this is a theorem we can get from the graph directly, which is if we observe all the parents of x, then we can simply do this to get the causal effect, which means just condition on all the causes of x. And then the do will give us this will give us the actually intended causal effect. Okay. However, this is not an interesting case because in reality, we often do not observe all the parents. So I will talk, so that's the interest case later. But let me give you some example now. Right. Again, fumigation and yield. Let's come back to fumigation and yield case. Right. Again, we're doing, we're doing RCT, we're doing, fumigation on yield. But now let's suppose we have some mechanism. The mechanism is how does fumigation actually affect the yield of crops, right? So I'm going to assume an underlying mechanism and let's see if we can get the causal effect out. So suppose fumigation is F, right? It helps control earworms E, okay? So E is earworms, and earworms affects yield Y, all right? So fumigation will control E, and E will affect the yield Y. And then when farmers decide whether they want to use fumigation or not, when they want to do this, it's affected by weather. So maybe maybe it's too hot, they don't want to use it. It's too cold, they don't want to use it. Whatever, right? So weather controls that, and it's also affected by cost C. If cost is too high, they don't want to use it. Right? Cost is low, they use it. And then finally, we observe the price of the crop. Okay, the price of crop. So the price is affected by two things. So the price of the crop is affected both by the price of the fumigants. Okay, so the C, the price of fumigants affects the price, and of course how much supply affects the price. Okay, right. So that's a little simple story about what's going on here. There's a better drawing, right? So weather affects fumigation. Fumigation affects the worms. How many worms? How many worms affect the yield? So the yield is a supply curve. So the supply will affect the price, but also the cost will affect the price, right? The cost also affects whether people use the fumigation. All right. Okay. So I'm interested in what is the thing I'm interested in? I'm interested in the causal effect of fumigation on the yield. Okay. So this link is what I'm interested in. The effect of F on Y. So F is a binary, it's 0, 1. So whether people use fumigation or do not use fumigation. So I'm interested in probability of Y, distribution of crop yield, conditional on do F equal to 1. This is what I'm interested in. Okay? All right. Now from the graph, you should be able to write this way. You should be able to write directly. You should be able to write the probability of Y conditional on do F equal to 1. Okay, is equal to the summation. So let me just assume everything is discrete. Okay, so everything only has the 1, 2, 3 level. So I can do the summation rather than the integral because integral, is messy to write. So okay, give me write Py given conditional F equal to 1. And conditional on weather, conditional on cost, and then probability of weather and probability of cost. The sum over weather and cost. We can actually immediately write it this way. And this is based on our previous result, which is if I want to know the causal effect of F on Y, all I need to do is to condition on all the causes of F. If I want to know causal effect of X on this, this on that, if we condition on all the causes, then we can get rid of the do. We can just make it into a statistical relationship. So Py condition F equal to 1, and condition on WC, because W and C are two variables that cause F. So once we condition on that, then the do can disappear. Okay, we can turn this causal relation into a statistical relation, and just add, just integrate with regard to the P, and that's it. Okay, right. Okay, so this is a very nice result. This result simply says if I'm interested in the causal effect of one variable on the other in my model, all I need to do is to condition on all the causes, direct causes of this treatment variable, and then just add them all together, and that will give me the desired causal effect. Right. As you can see, in doing this, I'm turning a causal relation into a pure statistical relation, and which I can estimate from data. Okay, so that's a nice result that we can have. All right. Now the problem is. What if we do not observe WC? Okay. What if I do not see any parents? Okay. So here, F is directly caused by W, and F is caused by C. What if W or C, we do not see them? In that case, how do we actually get the causal effect? Now, that's actually a more interesting criteria. Right? So for that question, I'm going to introduce two more results from the graph, from causal graph theory. The result is called the backdoor criterion and the frontal criterion. Right? So that sounds a little bit ridiculous, the name, but I will tell you what that means. When PA are fully observed, when the parents of X are fully observed, we can use this methodology to get the causal effect out. So we say that when the parents of X are fully observed, this causal effect is always non-parametric identified. But however, if they are not fully observed, then we can use the following criteria to see whether the causal effect is identified. Okay? The first criteria is called the backdoor criteria. So here's what the backdoor criteria is, which is the backdoor criteria is very cool, and we'll use it a lot, a huge amount in our analysis. And we'll see. Okay. So the backdoor criteria says, okay, if you have an X and you have a Y, and then let's say there is a potential causal effect from X to Y. Okay. Now this is not a backdoor path. What is a backdoor path? A backdoor path is any path between X and Y. Okay. Any path between X and Y that has an arrow that goes into this X. For example, suppose there's a Z. Suppose there's a Z, and the Z goes to X like this, and the Z goes to Y. Okay. Now this is a backdoor path because it's a path between X and Y with an arrow that goes into X. Okay. Now it can also be many. It can look like this. It can go Z to X, and then there may be a W variable that can go to Z. Okay. And maybe there's another P variable that can go to W, whatever. I don't care, okay? It can be anything as long as there is a path. And the path has an arrow that goes into X. That's called a backdoor path. Right? Okay. So the backdoor criteria says that if there's any backdoor path, if it is open, if it is not blocked, then X and Y will be correlated. Or it will induce correlation between X and Y. Okay? So that's the first result we have. Again, these are all results from the causal graph theory, which I'm not going to prove. Okay? But there are proof, and if you're interested, you can, for example, all these proof in Pro's textbook will contain this proof. So this is a formal result, which is in the graph, in the causal graph, if there's any backdoor path that is not blocked, then there will be correlation between X and Y. So, in order for, what happens when there's correlation between X and Y? When there's correlation between X and Y, the correlation Py given X is not Py given to X. Okay? Right? Now, if without a direct link, there's a backdoor path open, then there's a correlation between the two. If that's the case, the correlation between X and Y doesn't tell you the causation. Why? Because only this tells you the causation, right? Only this tells you the causation. So we're only interested in this link. All right, okay? So whenever there is a backdoor path that is open, then correlation doesn't imply causation. Which means, if we want to have the causation of X and Y, we need to block all the backdoor paths. So that is a very, very powerful and a very, that's a very interesting and very powerful result. We see this a lot. How do we block the backdoor path? Well, in this case, let's just look at this one. Z goes to X, W goes to Z, P goes to W, P goes to Y. Right? How do we block it? Well, remember, we said before that if there's on a path, if we have a path like this, if there is a collider on a path, then this path is automatically blocked. However, if you condition on it, it's open again. On the other hand, if there's something like this, right? If there's something like this that is open, but if you condition on it, it's blocked. What about this case? Okay, so it goes into this one, this goes into that. If this open, it says open. But if you condition on it, it's blocked. So in this case, we have an open path. How do I block it? I can do anything. I can condition on Z, it's blocked. I can condition on W, it's blocked. Condition on P, it's blocked. Okay? So I can condition on any of them, or I can condition all of them. If I condition all of them, then they are all blocked. So once they are blocked, then the correlation between x and y will tell you the causation. Because in that case, the only correlation has to come from this direct link. So that's called the backdoor criteria. And we say that if these variables can satisfy, we say these variables satisfy the backdoor criteria if conditioning on them give you the complete block. Okay, give you complete block. Right. So, you may be a little confused now. So what does that have to do with economics, or what does it have to do with what you have already learned? So here's the link. First of all, remember this simple case where z goes to x, z goes to y. Z is called a confounder, right? Z confounder. Now this is a backdoor path. I hope you already recognize that. This is a simple backdoor path because this is a path with an arrow that goes into x. All right? This path is open. So to block it, condition on z, and we're blocked. Okay? So the question is, do we observe z? Do we observe z? If we observe z, now we say in this case there's if z is fully observed, we say there is no unmeasured confounding, or we say there's selection on observables. If z is observed, then we say the causal effect of x and y is identified. Why is it identified? Because I know that So if I observe x, y, z, right? If x and y is all observed, then I know that I can get the causal effect out. How do I get it out? Condition on z. Okay? Sorry. So just, so the E in this case, Py given x will be equal to Py given do x. Or Ey, okay, so Ey given x will be given to Ey given do x. Okay? Because, sorry. No, I shouldn't have said this one. Py given x. Py given do x, but condition on z. So I know that once I condition on z, the correlation becomes the causation, right? So Py given do x, but condition on z will be equal to Py given x and z. Okay? Correlation equal to causation once I condition on z. I can replace the P with the E, of course, right? Expectation will be the same thing. Okay, so but what is the Ey given to x? What is this thing? Well, this thing is simply equal to Ey given to x condition on z, but then let me just just integrate with rest to z, right? Pz, and if I do this, then I get this one. But this is equal to Pz, and the summation equal to that. Okay. So I hope this makes sense. All right. So the causal effect we're interested in boils down to this thing and this thing. Now both of these can be learned or can be estimated from observation data, from the data. So we say in this case it's identified because we're able to get the causal effect from the observation of all the data. Okay. So this is the identification argument. But then the second step is we need to estimate it. Okay? Now, how do we estimate Pz? Well, Pz is just, the frequency of z in the data. So that's easy. How do we estimate Ey given xz? The simplest way to estimate this is to run something like a linear regression where y is equal to beta 0 plus beta 1 x plus beta 2 z. Okay? All right. So let me make one more link with what you are already familiar with economics, and then so that you know what actually we're doing. Because I think I need another lecture to fully explain all the details. In economics, what you do is this: you say ability, let's say ability. It will lead to education, and it will lead to earnings, And education, but we are interested in whether education has a causal effect on earnings. So that's our story. How do we get the causal effect of education on earnings? That's the question, right? Okay. Using this framework, using causal graph framework, we have two steps. The first step is identification. Can we actually get the causal effect from our data? How do we do this? How do we make the identification? Well, identification argument has no models, okay? No statistical model, no whatever. You don't need the linear regression. You don't need anything. You just look at this graph. Just look at this graph. This graph says education to earning has a backdoor path. This backdoor path is open. Okay? This path is open because we have, right? So in order to block the backdoor path, I need to condition on ability. Once I condition on ability, I will get the causal effect of education on earnings. Right? So in other words, the effect of education, the effect of earnings, okay, earning would be wage, of due education is equivalent to the effect of wage on earnings, but condition on ability. Condition on ability. All right? Times the probability distribution of ability in the population. But this is equal to, but once we condition on ability, the causal relation becomes the statistical relation, which is E wage conditioning on earnings and ability. So I can directly write it this way. So that's what the causal graph tells us. Okay, so this says, so from this we can make the identification argument. Are we able to identify the causal effect of this on this? Well, it depends on whether by observing all my data, I'm able to get this one and this one, which is the conditional probability of wage, conditional earnings and ability, and distribution ability. Well, can we get this from data? Depends on whether we see ability in the data. If we do not observe ability in data, then the causal effect is not identified. Okay? Which means that even if we have infinite data on education and infinite data on earnings, as long as I do not see ability, it's not identified. Right? So this is the first stage, okay, identification stage. Now suppose we actually have ability in our data, okay? Suppose we have ability. Suppose I have all your exam scores, and I think your exam score is a nice proxy for ability. So I see ability. If I see ability, then our analysis here tells us that this causal effect is identifiable. Once it's identifiable, we are into the second stage. The second stage is estimation, which is how do I get this? Okay, how do I get the expectation of income conditioning on education level and ability? So this ability will be your exam scores, right? How do I get this thing? Okay. Well, the easiest way to estimate this will be to run a linear regression, which is your income is a function of beta 0 plus beta 1 education plus beta 2. A will be your exam scores. And then you can do a linear regression, and this beta 1 will be what? Will be essentially the interesting causal effect, right? Okay. So now, I don't think today we have enough time, but next time I will try to, or we will hone in on this. But this is what you are doing in economics, which is when you estimate the causal effect of education on your earnings, you are running this regression, but you are controlling for things that you think are endogenous, controlling for a confounder, right? So here the confounder is ability, which you use exam score. Right? So you are doing this directly in econometrics. But here what I'm trying to say is there are actually two steps. The first step is does this tell me causal effect? Right? Does this actually tell me causal effect? This step is based on the underlying causal graph. The second step is how do I estimate this? Well, the second step you can use a linear regression, but you don't have to use a linear regression. How to estimate? Well, you can use a random forest. You can use a neural network if you have learned how to do it. All right? The second step is completely flexible. You can use any statistical model to estimate this object. as long as you're sure that this object tells you something about the causality. Now, how do I know this object tells me something about causality? Based on our first stage causal analysis, which is based on this graph, I know that once I condition on ability, the result is correlation implied causation. That's why I know once I condition on ability, this statistical relation tells me something about causality. Okay, so that's but it's okay if you don't completely get it, because I'm going to spend more time on it next time. Okay. All right. Let me see. I think I'm ready to finish it today at here. Judging from your response, I think most of you are pretty confused back to this lecture. But I'm going to leave it here, and I'm trying to do a better job next time, go deeper into this. But let me just say finally, just two definitions, okay? X and Y, okay? Now, X is set to be, previously I said, suppose I give you a graph, X and P, whatever. I think it's the entire graph. Now, on the entire graph, if a node, so on the entire graph, if a node has no parent, this node is called exogenous. If that's parent, it's called endogenous. However, when we say exogenous here, we say it's exogenous to this graph, or and X is endogenous. It's endogenous to this graph. Okay? So now I'm going to say that I can also define endogenous or exogenous when we say it's to a certain variable. So X is exogenous to Y if there is no open backdoor path. Okay? So here, is there open backdoor path? Yes, this is the open backdoor path, this is the open backdoor path. So if I condition on Z, if I condition on P, then X is exogenous to Y, because there's no backdoor path from X to Y. Otherwise, X is endogenous to Y. And I will show you that this definition of exogeneity and endogeneity is exactly the same definition that econometricians talk about. Okay, in economics, when we say some variable is exogenous or endogenous, we are actually talking about whether the backdoor path has been blocked or not, which I will leave for next time. Okay, not this time. So that's all I want to talk about today. Maybe we can finish it a little early. Next, I think you guys are a little bit confused today. Next time I'll try to do a better job explaining everything. Okay. All right. So let's continue next time. Yeah.